Hi, I'm Saima Badar, and welcome back to another episode of the Elevator Problem series. In today's video, we are going to explore something we all experience but rarely question. Why our weight seems to change inside an elevator. Have you ever stepped into an elevator and suddenly felt heavier or sometimes lighter? Did your weight actually change? Or is something deeper happening? Today we are going to uncover the physics behind this feeling and then solve a real numerical problem step by step. Let's start from the basics. The weight of an object is the gravitational force with which the earth attracts or pulls it towards its center. Mathematically, it is expressed as the product of mass of the object and the gravitational acceleration. So if a person has a mass of 60 kg and gravitational acceleration is 9.8 meter per second square, the weight is 60 multiplied by 9.8, which is equal to 588 newtons. This is the actual weight of the person. And here is the key idea. This does not change unless your mass or gravity changes. Now here is the surprising part. You don't actually feel your weight. What you feel is the normal force, the push of the ground or the elevator floor on your body. Weight pulls you downward, whereas normal force pushes you upward. When you are standing still, the normal force is same as the weight of the object. That is mass multiplied by the gravitational acceleration. So your apparent weight is same as actual weight when you are in a stationary frame of reference or your frame of reference is moving with uniform velocity and everything feels normal. But what happens when you are in an accelerated frame of reference? That is, your frame of reference is accelerating or decelerating in upward or downward direction. Let's step into an elevator. When the elevator accelerates upward, your body must accelerate upward too. So the floor has to push you harder. And according to Newton's second law, the net force in upward direction is equal to the difference of the two forces acting on the person. One is the normal force which is acting in upward direction and other is his weight in downward direction. So the net force on the person will be equal to mass times acceleration of the elevator, which in turn is equal to the normal force acting on him in upward direction minus the weight of the person in downward direction. So rearranging this equation will give us an equation for the normal force or the apparent force of the person as mass times the gravitational acceleration plus the acceleration of the elevator. So we can see that instead of getting mass times gravitational acceleration, we get an equation for the normal force or the apparent weight of the person as mass times the gravitational acceleration and the acceleration of the elevator. So we can see the apparent weight increases or you will feel heavier in an accelerating elevator which is moving in upward direction. So you have observed that the weight of the object will appear more or greater in an accelerating elevator which is moving in upward direction. But what will happen if the same elevator which is moving in upward direction, it decelerates, it slows down? Now this is subtle. The elevator is still moving upward, but its velocity is decreasing. This means that the acceleration is actually downward. So again, using Newton's second law of motion, we will derive an equation for the normal force. But now here in this case, we will use negative acceleration because it is deceleration. So using the same equation, F net is equal to n minus mg, we'll use minus times ma equals to n minus mg. So rearranging this equation will give us an equation for the normal force. And the equation for the normal force as mass times the gravitational acceleration minus the acceleration of the elevator. So apparent weight decreases and you will feel lighter here in this case. Now what happens if the acceleration of the elevator is zero, whether it is moving in upward direction or downward direction? So here in this case, the net force on the elevator or the person is zero, and we will get an equation for the normal force or the apparent weight of the object as m times g. That is, the normal force will be same as the actual weight of the person, and you feel normal. And if the acceleration of the elevator is same as the acceleration due to gravity, which is directed in downward direction, so here in this case, the normal force on the person will be zero and he will feel weightless. So your actual weight never changes. What changes is your apparent weight, the force you feel. Now let's have a numerical challenge. A person of mass 60 kilograms stands in an elevator accelerating upward at 2 meters per second square. Find the apparent weight or the normal force. Now let's solve. As the elevator is accelerating in upward direction, so we will use the equation that we have already derived for the normal force or the apparent weight of the person as m times g plus a. So putting the values, you are given all the values. Using all these values in the relation, we get the normal force or the apparent weight as 708 newtons. On the basis of the values given, if you see your actual weight is 588 newtons, but it appears as 708 newtons in an accelerating elevator which is moving in upward direction. Both are different, not because gravity changed, but because the floor is pushing you more in an accelerating frame of reference. So you see that your mass is same, gravity is same, but a completely different experience because physics doesn't change reality. It reveals what was always happening. If you have understood the concept, then let me leave you with the question of the day. What will you observe if the elevator is moving downward and it either accelerates or decelerates? Will you feel heavier, lighter, or the same, and why? But do remember that it's not about the direction of motion, it's about the direction of acceleration that determines the apparent weight of the person in an accelerating or decelerating elevator moving in either direction. So now, the next time you step into an elevator, you won't just feel the change, you'll understand it. If this helped you see physics more clearly, don't forget to like, share, and subscribe. I am Saima Badar. See you in the next episode.